Now let's have a look at inter-process communication. In a computer system, some of the processes would be independent, whereas some others would be cooperating. By independent processes, we mean those uh, for which the order of execution would not be important. For example, consider three processes, P1, P2, and P3. If the results, the outcome of these three processes is always the same, independent of whether you execute these processes in the order P123 or 321 or 231, doesn't matter, it's always the same, then we can easily say these processes are independent of each other. However, in some cases, we will have some processes that are dependent on each other. Typically, they would be dependent because they are cooperating. So in this case, it would be important whether P1 executes before or after P2 because P1 would be modifying either a variable or some file or any other data on which P2 depends. So it would be important if P1 modifies that data before P2 makes use of it or not. So the reasons for the cooperation of these processes could be that we want to share information between the processes because they are doing something together typically. This helps us to speed up computation. For example, if you need to do some, say, I/O operations, like, say, a database system, you can either do things in a serialized manner. That means if you have, for example, 10 requests, like 10 queries that you need to execute on the database, 10 questions that for which you want to find the answers. If you solve them, if you respond to these queries in a serialized manner, that means you should first try to find the answer for query 1, then go to query 2, 3, 4 in this order. But in that case, uh, while the system is trying to access the database for query 1, query 2 has to wait. However, it could be possible that query 2 depends on, for example, a different table, or it could be working over a different disk. So it could be possible to run these in parallel, or doing something before the other might help us in queuing. In such cases, we would achieve some computation speed up if we do parallelization. Also, it would help us in software engineering because we now have a more modular design. For example, while writing the software, the program for the user interface, for the front end, you use different tools and you need different experiences, whereas it's quite different for the case of a backend, for network operations, for database operations, whatever. So, for example, if you have a large project, you could give the part that's related to the front end for your front end design, to your front end designer, whereas give the network operations to the network guy and backend processes to the backend guys. So this also provides us modularity and also convenience. Therefore, typically large projects will be composed of several processes that are communicating in between. And this is what we call inter-process communication because this is communication between the processes. And we have two different models for doing this, either shared memory or message passing. The figure on the left is for message passing. For the sake of the example, we have only two processes here, process A and B. They communicate with each other over a message queue, over a message box, in which the messages are ordered. So the message box, the message queue would be initially empty. You can look at all of these messages just like a sheet of paper, okay? And these are enumerated. So initially there was nothing there. So when process A wants to send a message, it just writes it on a piece of paper and enumerates it as 0 because there's nothing in the message queue and places it there. So this would be our message 0, M0. Another one comes as M1, M2, M3. And if you want to read something, you will start from the first one, which is M0. Okay, so the messages could now arrive at the message queue in at any time, and you could also read from the message queue at any time, but you would always be reading, for example, in the order they were placed there, which would be in this case a FIFO queue, a first in first out queue, or FCFS. We also call that FCFS, so first come first served queue. Of course, we do have different queuing principles, but the most basic one would be that. Another approach would be the shared memory approach, which is the case on the right. So again, we have two processes. Process A has its address space, this blue box, and process B has its own address space here, again, another blue box. Actually, the shared memory, which is shown in between, it doesn't have to be in between, but the shared memory is actually in the address space of both A and B. So in fact, the address space of A would be this blue box plus the shared memory, and similar would be true for process B. Now you should be very careful with shared memory access, because if two processes try to access the same variables, the same data at the same time, the outcome would be could be quite different depending on which was scheduled first. So we'll come to that in more detail soon. So now we can talk about the famous producer-consumer problem. What does the producer-consumer problem mean? Consider a problem, a scenario where you have one or more producer processes, and again, one or more consumer processes. Okay, so let's first have an analogy. For example, assume that, consider, for example, a bakery shop. Okay, so at the back of the shop, someone is producing, say, bread. Okay, so every time the guy behind produces bread, he or she brings several, one or more loaves of bread and places them on the counter. Okay, so that guy is the producer. Note that there could be several producers, so several people could be preparing bread, so they would all bring it down. Now, in that case, the bread, if you look at the bread loaves on the counter, some of them could be produced by producer 1, let's call that P1. Some could be produced by producer 2, P2. Okay. Now, there would be also consumers, people coming in and buying bread. Now, they would be the consumers. So let's call them C1, C2, C3. So in this case, the consumers do not care who produced that loaf of bread. So when you're buying some loaf of bread, it could be anyone on the counter. Well, to go in an ordered fashion, you would be, in this example, picking the first available on the counter. So it's just like a queue. The new loaves of bread are placed at the end of the queue, and the consumers take the breads from the beginning of the queue. So that would be a producer-consumer scenario. In our case, instead of loaf of bread, we're producing data, message, whatever. There are processes that are producing the data, and that there are processes that are reading the data. So the ones that are writing the data, they're producing and writing the data, would be the producer process, and the ones that are reading would be the consumer process. And as I said, you could have one or more of any one of these processes. Now, that counter in the case of the bread scenario would be actually our buffer, because the bread would be produced at its own rate, depending on how fast the oven is cooking the bread. Okay, whereas the consumers, the customers, are coming in according to their own plans. It's not like if a bread is being produced, say, every 1 minute, a customer is entering the shop. That's not true. Okay, so it could be that the producers keep on producing bread, and see, initially there was no bread on the counter, so you produce one bread and you put it here. Before somebody purchases that, you produce another one and put it next to that one. Next, next, next. And then some customers may come one after another, and they may consume the breads in a rate faster than the rate you're producing in. Okay? Now, when you're producing the bread and you're putting them on the counter, what is the size of your counter? Is it finite or is it infinite? Now, in the case of a finite size of the counter, we are talking about a bounded buffer. Whereas if it's infinite, we would be talking about an unbounded buffer. Of course, there is no counter of infinite size, but if the counter is large enough so that you never hit the case that a producer produces bread and there is nowhere to put the bread. In that case, we can say for all practical purposes, we may assume the buffer or the counter is infinite or it's unbounded because we never hit the bound. So practically for us, it would be unbounded. Whereas if the counter is limited and if it gets full of bread, the producers will have to stop and wait. They cannot continue because if they continue, they would be left with the bread in hand. They cannot put it anywhere. Okay, so that would stop production. On the other case, it is possible that a consumer walks in to the bakery shop, wants to buy some bread, but there is no bread produced yet. So in that case, the consumer would have to wait. That person would be blocked until some loaf of bread is produced by P1 or P2, it doesn't matter. But there should be some bread produced. And the bread produced would be placed on the counter, and immediately the consumer would take that bread and leave. Now again, we have no bread on the counter, but at least we don't have any consumers waiting now. Okay, that's how things are running in the case of a bakery shop. In a similar or analogous way, we can have processes that are producing the data, and we can have other processes that are reading the data. So we can implement this scenario in two processes, what we call the producer process and the consumer process. But they need to share some buffer, which is the counter there. Okay, so for that, typically we will need an array. So that would be an array of items, like in here, our buffer is an array of item. Well, how many of them? Well, the size is given in a constant here, which is set to 10. It could be anything, whatever you wish. But in this example, it's set to 10. And each item is of some data structure. I don't care what. Okay, you can define anything. It could be, for example, student record about the department, about any goods, whatever. So we have enough a buffer of size, buffer size, and we need 2 pointers. One is the index of the place where the next item is to be placed, because the producers need to know where they should put the bread when they come to the counter. Okay, so the in pointer is for that, because you're putting into the buffer. And for the consumers, again, you need a pointer, an index into this array that shows from which address, from which element you should take the next one. Initially, there's nothing in the buffer, so they're both initialized to 0. So now we can talk about the producer and the consumer processes. So in the case of the producer process, continuously, that's why we have an infinite loop here, continuously you would be producing an item. So the guy would be producing an item and putting the outcome into a variable, say next produced, which is of type item. So you produce the item and it will take some time. I don't care how long, but producing the item will take time, and when it is done, it will be in that next produced variable. Now here, of course, you don't have the comments. Instead of the comments, you have some code. That's whatever it is. We don't care about that part. And once the item is produced, I should check if I have place in the buffer. Okay. If I don't have place in the buffer, remember this. If I don't have place in this buffer, I have to wait. As the producer, I have to wait until some space is opened in that buffer. In the case of the consumer, I would have to wait until something appears on the buffer. That will visit soon. So while the position remember the in variable, which is initialized to 0, while in +1 modulo buffer size. Why is that so? Because our buffer, now we have an array. It's just like, let me draw it here. 1 second. Let me grab the pen. So this is our buffer. Let me just show it with B. With the index starting from 7, 8, and 9. Okay, we have 10 elements in our buffer. We have the variables in and out. Sorry. Both initialized to 0. Okay, and currently the buffer is empty. So now, if you look at the loop here, while in +1 modulo buffer size. Why is that modulo? Because I'm using this buffer in a circular manner. So when I reach the end, I will be able to start at the beginning. For the moment, buffer size is 10. Since in is 0, 0 plus 1 would be 1. Modulo 10 doesn't matter. It's still 1. 1 is equal to out. That's not true because out is 0. Okay. 1 is not equal to 0. Therefore, I can proceed. This actually checks if I have space in the buffer. Okay. So I would be producing something. Let's say I have produced A. So I produce A, item A, whatever A is, in the buffer, in index 0, because in is 0, and then increment in by 1 in a modular fashion with modulo buffer size, but for the moment it doesn't matter. So it becomes 1. Okay. Before a customer arrives, if the producer produces another variable, sorry, another product, it would be placed here, again in index in, which is now 1. So in becomes 2. Another is produced, that is placed in C. Okay. And meanwhile, let's say now at this very moment, I have A, B, and C in the buffer. Note that in is currently 2. In after 2 has been placed here. Since I have the increment here, it would be 3. Sorry. So in is 3, out is 0. And let's say a consumer arrives. And the consumer will first go into this loop. Not in that whole loop, but let me just correct that. Enter this loop while in is equal to out. Is in equal to out? No. Okay. In is 3, out is 0. So it will just skip that. This is actually checking whether there is something in the buffer or not. Okay. When there's nothing in the buffer, it would just be turning in this loop. Okay. So when there's something in the buffer, in and out would be different values. So next consumed would be taken from buffer out. Okay. Therefore, we would take the value from, let me take the pen, we would take the value from where out is 0. So we would take the value, I forgot to pick the eraser. Sorry. We will take the value from index 0. So we will take the value A, okay, and also the variable out is incremented by 1, so it becomes 1. So if another consumer arrives, or the consumer process keeps on consuming data, it would be taking the data this time from index 1. Okay, so it would be removing B and incrementing out this time to 2. So it would be, rather than deleting, let me just scratch it. So it would work this way. Now note that it is possible, for example, for the producer to work in a very fast manner. So let's say it goes as D, E, F, G, H, I, J. Okay. And also, let me just clean out that one I have crossed out. So it also produces K. Okay. Now at this very moment, you should be careful because what will happen right now is how much of the buffer is used. I had 10 positions and 9 of them are already in use. I have 9 products waiting for consumers. And assume the producer produces yet another item. Okay. Now, what's the, by the way, the value of I would be what? I is the position to place the next value. So it would go this way all the way, and I would be 1. Okay, because we expect to put the new value in index 1. And our out is still 2 because no consumer has arrived yet. Now at this very moment, what will happen is the following. If you look at here, in plus 1, in is, remember, 1, plus 1 is equal to 2, modulo 10 is still 2. Is it equal to out, which is 2? Yes. And we will get stuck in this loop. Okay? So we will get stuck here. We cannot proceed. So it looks like we enter an infinite loop. Actually, the producer really should wait until some consumer takes in some data. Since the consumer is yet another process running in the same operating system, so the scheduler might schedule the consumer process, which is a separate, related, cooperating, but it's a separate process. The consumer could work, and when the consumer wants to consume some data, it would enter again the loop. If is in equal to out, well, in is 1, out is 2. They're not equal. Pay attention. Here we were comparing in plus 1 with out. Here we compare in and out. Okay. Since they're not equal, the consumer does not need to wait, because it would be waiting only if there was nothing to consume, and there's plenty to consume at the moment. So it will take something from out, which is in index 2. Okay. So it would take out C, okay, in index 2. So let me grab the eraser again. So it would consume C from here, and then it also comes to this line which says out is incremented by 1. Therefore, this will become 3. Okay? Now, when this becomes 3, pay attention. The producer process is also running. When the CPU schedules the producer process, although the producer process was stuck here in the while loop, now it will find that out is 3, but in is 1 plus 1, it's 2. 2 is equal to 3. Now the condition suddenly became false. Producer did not do anything. Actually, it was consumer that modified the producer. But since the variables they are sharing are in the shared memory, the change made by consumer would affect the producer. So now the producer would be able to put a value in what? In the in index of buffer, which is 1. So the new value L will be placed here, and in will be incremented by 1. Again, if the producer wants to produce something else, again it has to wait. But at least we never overwrite anything. Okay? Such an example typically works, for example, in the case where, consider like you have a process that is running slowly because it's doing something very complex. And we have a very fast network, and its fast sender is sending data over the network to this process. Now, if the fast sender is sending data too fast, the buffer would be full very fast. And the sender cannot send more data until the consumer reads something from the buffer. As soon as the consumer removes something from the buffer, the sender can send a little bit more, but will have to wait until the consumer consumes some data. In this way, no data would be lost because the rate at which the sender and the consumer here, their rates are different. They're running in different speeds. That would not be important. Still, we wouldn't overwrite any data because we will pause the fast sender when necessary. Now, if the sender is slow, but the consumer is fast, in this case, the consumer would consume all the data in the buffer. But when there is no more data to read, the consumer would just pause and wait until the sender sends in something. And when that happens, the consumer again immediately can take that data and process, and again wait if the sender is going slowly. And note that the rates at which the sender and the consumer are working could vary in time, but this process will run very smoothly.